In this lesson, we're going to look at how we can use Gauss's law and apply it to the case of a charged conducting sphere to predict the electric field on the inside and the outside of the sphere. So what we have here is, in gray, is a sphere, and we'll put a total charge of plus Q on that sphere. And since this sphere is conducting, all of the excess charges are going to repel each other and get as far away as possible. And so the idea with this would be that if I'm putting positive charges on this, you can imagine the positives are going to go to the outside of the sphere, like so. From a physical point of view, we know that positives themselves don't move, but positives can be thought of as kind of the holes that are left by electrons when electrons move. So what's happening in this case is if you put a positive charge on something, you're actually taking electrons out of it. And the holes that remain are going to spread around because the electrons themselves will spread around to make that happen. So if you're wondering about that, that's what actually happens. So we'll put a radius on this object here. That's our capital R, and we've got Q that's going to be spread around. So the goal with this is again to derive the electric field, and we're going to derive it as a function of R of lowercase r, and lowercase r is going to be the radius of the Gaussian surface. And so that's my Gaussian surface is going to be this dashed circle. It's actually a sphere because this is a three-dimensional situation. And the reason we picked this spherical geometry is because the electric field is going to be everywhere perpendicular to that Gaussian surface. And that means that when we take the dot product of the dA vectors with the electric field, that the dot product will always be the dot of two vectors which are pointing in the same direction, which means that it's the cosine of 0, which is nice. The other nice thing about choosing a spherical Gaussian surface is that these electric field values, the sizes are the same any place on that surface. So you're guaranteed that as long as your Gaussian surface is concentric with the charged object. The solution to this problem is actually very much like the solution to the earlier problem that we did for a shell of charge. And what we do is that we break up the radius of the Gaussian surface so that we look at radiuses which are smaller than the radius of the conductor, in other words, inside the conductor. The idea would be this. I didn't draw it, but I can draw it right now. That Gaussian surface would be a sphere that's inside of this solid conductor, but all of the charge is on the outermost skin of the conductor. And so for anything on the inside, we can use kind of the logic of a charged conductor to conclude that there would be no enclosed charge, okay? Because all Q is on the outside. And so for that reason, when we set up and write down Gauss's law, we would be in a situation where we have an integral equal to 0, the integral over a spherical surface, and the only way that that can happen is if the electric field is equal to 0 inside. So the electric field inside is equal to 0 for all r less than r. And that's a lot like the shell of charge example from earlier too. If you go outside, if you come out here, this is your outer Gaussian surface, then of course you're enclosed charge is Q, and so you end up with that, because now that's all of the charges inside that Gaussian surface. And we actually solved this integral before, and we said that the E can come out, and you're left with the integral of the surface of a sphere. So that gives you the E times 4 pi r squared equal to Q over epsilon 0. And that really just gives you the standard formula for a point charge. So what's interesting about this is that if you have an object like a conductor and you put charge on it, if you're outside of that object, all of that charge acts as if it were concentrated at a point. Okay, so it's like as if all Q was kind of concentrated, right, at the origin. So if we make a graph here, as we've been doing, E versus R, where this is the radius of the conductor, we of course would have 0 up until that radius, and then you get a sudden increase, and this is going to be KQ over R squared. Okay, and that happens at this point right here. That is not infinity here, right? If you substitute in R, big R, you would find out that that starting point is KQ over big R squared, and it comes down. So once again, this is the exact same result that we got for the shell of charge. The result is that you get a chunk that kind of gets taken out from 0 to big R. So the function normally would continue up to infinity, but it can't now because you're blocking the field inside. Okay? So that's that example. Very much like the other one, and hopefully that makes sense to you.